Welcome, gentlemen, to your first video of the year on Verso. Today we're going to study binary compounds, more specifically covalent compounds. So we're going to learn to name them and also come up with the chemical formula from the name. So the first thing to remember that in a covalent compound you're dealing with a nonmetal and a nonmetal. And so electrons are shared between the two compounds in this case. Okay, between the two nonmetals. This is an important distinction because when we compare ionic and covalent compounds, there's a huge difference, and it comes right down to the naming. One of the main differences here in terms of covalent compounds is that there's a prefix in the name, and certainly in the second element in all of these cases. Okay, so the steps here in terms of naming are going from a name to a formula in a covalent binary compound. The first step is to write the symbol of the first element, followed by the number of atoms present, as indicated by the prefix in the name. Then write the symbol of the second element, followed by the number of atoms present, as indicated by the prefix in the name. So very simply, you're just writing the two symbols from the periodic table, just like you did in the ionic compound. And rather than figuring out oxidation states, you're just going to use the prefixes to determine the number of each element. Okay? If you're going from formula to name, it's very similar, just the reverse, right? So write the prefix for the number of atoms of the first element, followed by the full name of the first element. If there's only one of them, you can ignore mono. Then write the prefix for the number of atoms of the second element, followed by the first syllable of the second element, and then just like we did with ionic compounds, you're going to add "ide." Okay, so all formulas of covalent binary compounds are not reduced to lowest terms, and this is important as we start doing Lewis diagrams later in the unit. You'll see, but because there's this sharing of compounds, there's no more this lattice structure of repeating units, and so they're individual molecules. And a C2H4, for example, is a very different molecule than C4H8. Even though they can both be reduced to the same numbers, they could obviously both be reduced to CH2. It doesn't work that way. They're very different molecules. Whereas you would see here, CH2H4 looks something like this. A C4H8 will look something more like this. So you can see the difference between these two molecules is very significant, and so that's why we are unable to reduce in these cases. Okay, so the prefixes, you're probably familiar with most of them. Mono is 1, di is 2, tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. Okay, so you'll have to memorize those along with sort of how you use the periodic table to find them. But other than that, it's pretty straightforward. Okay, so we'll start here with our first example. We're going to go from formula to name. So CCl4, the first element here is carbon, so we'll just write carbon. It's a mono, it's a single element, so we're going to drop the mono in this case. So normally you would write mono because there's one of them. We're going to ignore that in this case. We assume if the first element doesn't have a mono in front, it's a single. Okay, and then it's chloride. There's 4 of them. If you remember, 4 is tetra, so we go with tetra. Cl is chlor, and we're going to use the suffix "ide." So this becomes carbon tetrachloride. Okay. The next example, similar idea. There's 1 sulfur, so we're going to drop the mono in this case, so it will just be sulfur. Sorry. I don't know why that's doing that. There we go. Sulfur, and we have 3 oxygens, so it becomes tri-oxide. So again, we drop the suffix, replace it with "ide." So sulfur trioxide in this case. Okay, going in the reverse direction, we have carbon. There's no prefix, so we assume there's one of them. So we have C, we have a disulfide. So again, we must have sulfur, which is S. Di tells us it is 2. So we have CS2. In our final example, we very clearly have a prefix, penta, which means there are 5 phosphorus atoms. So we're going to put a P, we have 5 of them, and then we have decoxide. Deca, if you remember, was 10, so we have 10 oxygen atoms. So P5O10 in this case. Okay, so hopefully that's pretty clear. In terms of naming gases, so diatomic molecules, if you remember from grade 9 and grade 10, a lot of the gases over here in your periodic table, nitrogen, fluoride, sulfur, chlorine, bromine, iodine, all these guys, and even hydrogen over here, they never travel alone. They're so reactive, we don't see them alone in nature. So they travel as diatomic molecules, as we call them. Di, 2, atomic atoms. So you have 2 atoms, diatomic gases. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are examples of this. Okay, in terms of the noble gases, they're going to be monatomic. You remember mono, 1 atomic atom. So in the case of the noble gases, we have 1 atom in these cases. They're so unreactive, they don't react at all. And so they're almost exclusively, they travel by themselves. Okay, so it's very clear. There's a very clear distinction. These guys, and actually that's a mistake, right? Sulfur was not part of that group. So you're going to go, so this group here, along with hydrogen, are diatomic, and then our noble gases, because they don't react with anything, are monatomic. And that's the clarification. Okay, so to review, covalent compounds, 2 nonmetals sharing electrons. We use prefixes to clarify, right, how many of each atom are present. Diatomic gases, most of these gases in the nonmetal area, and hydrogen travel in pairs, and the noble gases travel alone. Thank you, gentlemen. I hope this was useful. We will review this in class.